So very warm evening to one and all present here. Am I audible, Rashi?
Yes, you're audible, Aishwarya.
Okay, thank you. So I would like to extend my heartiest gratitude to all of you for joining us today for this wonderful webinar on asset management with power system application. So before we start the session, let me take a moment and welcome everybody. So first and foremost, I would like to welcome our honorable guest of today's session, Dr. Lina Berling-Jenberg, Professor in Power Grid Technology at KTH Royal Institute of Technology. A heartfelt welcome to you, ma'am. I would also like to welcome our chapter advisor, Dr. Arun Kumar Patil, and our IEEE Student Branch Counselor, Dr. Abeksha Madhukar. A warm welcome to you, sir and ma'am. I would also like to welcome all the participants and volunteers to today's session. A lively welcome, guys, and happy learning. But before we dive into the talk, here's the format to give you an idea of what to expect. We will take a few moments to introduce our guest today and tell you a little bit about their background in the industry. We will then start with the talk, and then the second half of our time today, we will open up the floor to allow you to ask specific questions that you have. Okay, guys, so let's go ahead and get started. Today we have with us Dr. Lina Bertling-Jenberg, the Director of Energy Platform and is the Coordinator of Lifelong Learning at Electrical Engineering and Computer Science School. She completed her PhD in Electric Power System at KTH in 2002. She has been the chair of the Swedish PE or PEL chapter for 2009 to 2019 and has served in the governing board IEEE PES for 2012 to 2016. She also has been an editor for the IEEE Transactions on Smart Grid Technologies and chaired the first IEEE ISGT Europe conference. We are highly honored to have you here with us, ma'am. So now I would like to request our chapter advisor to have a quick word and welcome our today's guest.
Good evening to all. Am I audible, Rashi?
Yes, sir, you're audible.
Yes. Thank you. Thank you. Good evening, ma'am. Professor Lina, ma'am.
Good evening.
Heartily welcome you for this August gathering or the event on asset management. I hope you know I am Arun Kumar Patil, Chapter Advisor, PES, Central University of Karnataka, madam. And I also heartily welcome all the participants and the organizers of this event. Before we move on, I will try to tell how much important is asset management, especially for power sector now. Because the prosperity of the nation is defined by energy consumed by per person or per citizen of the nation. That is, per capita energy consumption is directly related to prosperity of the nation. That is why all the governments are investing lot of money on developing infrastructure for power sectors. They are building power plants, they are building transmission lines, they are building substations, many things. In some countries, government is directly investing. In some countries, private people are investing. And still, we are facing problems in power sector. And with sufficient infrastructure also, we have many problems in the power sector. In that case, asset management plays a very vital role. Especially we in India, we have experienced many situations like transmission line congestion. We have transmission lines, but at certain moments, transmission line becomes overloaded, or sometimes we have transmission lines, but we don't have power. Then scheduling of the maintenance of these equipments of the power system, when to maintain, what time we have to keep them for maintenance, because Power is required 24 into 7, 365 days. For all these reasons, maintaining assets of the power system is very important. If we maintain them properly, then only we can expect good service from those equipments. With this background, I will request Dr. Leena Madam to enlighten our participants on asset management in power system. I heartily welcome Madam. Thank you. Thank you all. Madam, the floor is now open to you, Madam. Thank you. We can start, Madam. Thank you.
Thank you so much for these introductions, and thank you for welcoming today. It's a pleasure to meet you all. Even though I can't see you all, I'm very excited to be here. So I have prepared a presentation. I will share the presentation afterwards, and you can be able to share it with all your colleagues and friends. And I will turn it up now. Let me see. Can you see my screen now, my talk?
Yes, ma'am, it's visible to us.
Okay, thank you so much. So first of all, again, thank you so much for inviting me today. And obviously, it would have been even much more nice to see you. And now I see a picture of myself. But I want to tell you that if you want to ask any questions, you're just welcome to tell me anytime. And I prefer hearing something, but not hearing anything. Okay. So I wanted to start and show this picture. This is from a very great moment when I was visiting in Bangalore in India, and it's for the ISGT in 2013. You can actually find me here in the middle, and we were dressed up in traditional clothes. It's a very, very nice event. And I think one of the parts of being a member in IEEE and society is being able to come and meet you. And I look forward when we can start to travel again and meet in person. So for today, I have prepared my talk, and I will start with a brief introduction and motivation of the topic. And I really appreciated the introduction speech here. And it's very interesting to hear about the specific challenges that you are facing. And I look forward that we could have a more discussion later on also to relate my presentation to that. And the material included in my presentation is quite extensive. The reason for that is because I also give a full day tutorial in this topic, and I have decided to keep a little bit more material than we will go through in detail, and I will share it with you afterwards. So it's my plan that some of the material I'm using as a reference, and you can look later on. So I will start with a brief introduction and motivation, and then I will just say very short about some ongoing activities that I think could be interesting to know what's happening now. And then I will prepare a material where we will discuss about the terminology, the tools, the methods that I've been working with, where we relate reliability and maintenance. And following that, I've included a couple of case studies, and here are selections that you can be able to read afterwards. But I would also like to save a little bit of time so we can have a discussion. Today, I think at many places in the world, we are really trying to focus our mind on what are the overall goals. And the Sustainable Development Goals is a way to push all of us, independent on where we are or who we are, and trying to make a better world. And for us working in the power energy society, I think all of us feel that we can really contribute in a lot of these different aspects. So obviously it's for affordable and clean energy, but it's also related to where you are in the world on the other aspects. We see the sustainable cities, etc. But also possibilities to contribute to electrifying at places where we're not electrified, etc. So currently I'm involved in an international group. It's a CIRED group. Some of you might be aware about CIRED. In the sector of the power, we have two independent groups, except IEEE, of course, IEEE PS. But as an engineer, many are also involved in either CIRED or CIGRE. So CIRED is it's an organization that focuses on the distribution level, and the CIRED arranges a conference every second year. It will happen this year. CIGRE, on the other hand, is a little bit more expensive organization that do also kind of working groups. But I wanted just to mention here that I'm actively working. I'm the convener of a group in CIRED, which is very much related to the topic we talk about today. And I thought it would be of interest for you to know this. So if you are interested in this topic, you're very much welcome to contact me. So the purpose of this working group is that we are trying to identify experience and best practice in the topic of lifetime extension. I will come back to this obviously in my presentation, but we see that one of the developments now is that it's not enough anymore just to say that we are building equipment and we are running it to end of life. Now we see in what we call a circular economic perspective that we want to extend the life, we want to reuse material, and we see that we have a more circular perspective of how we work in the society and all kind of perspectives, including, of course, the technology. So I wanted to mention that. In the beginning of the year, one of my PhD students, she presented her work, and I also wanted to share that with you. And here is her thesis. So we have worked together for many years on condition monitoring, and this is applications for wind turbine. So this was presented in the beginning of the year. And some of the results that I show at the end is publications that we have are part of this thesis. So there are three key messages that I really would like to give and share with you, to bring with you after this presentation. The first one is really the value of making smart decisions. And this is motivating the reason for adopting asset management. So in a way, if we fully understand what it means, asset management, what that word really means, then we also have the knowledge of that is what we should do, because it's the only smart way to do. Because the context is really that we are doing something actively that's increasing the value of the assets we have. Depending on the circumstances, we will do it differently. But the whole purpose of it is to add a value. So I think that's really a main key message. My other key message is that we need standardization. This is needed, this is crucial for success. The IEEE organization that we all belong to are making very important contributions in the standard development. And when we are in the world today with very fast changing technologies, very many new developments, standardization is very crucial, making this happen. And my third key message, that's more related to my own research and the more smaller context where we try to contribute. And this is where we relate reliability analysis to the preventive maintenance. And that will be a tool for asset management. A little bit more specifically, what the new activities are that I mentioned before is that we are working on machine learning methods for condition monitoring, and we have applied this for different wind turbines. And here is also a book that I was happy to publish a few years ago, which is collecting a main of the publications that's been done together with my students within this work. And I believe that in the topic of asset management, the key is really like that we learn about the experience, what we have done, because many times we are constrained that we don't have the data, we don't have things. So the best we can do is to learn what we have done in past, what others have done. So I think it is very important that we share our experience. I also like to start with an acknowledgement, because this book and all my work has not been possible without the support of my mentors. And when I was starting my own PhD student work many years ago, I was very fortunate to have very nice professors working with me. I had in power reliability a Professor Ron Allen from Manchester, and which eventually led me to his best friend, Professor Roy Billington in Canada, in Saskatchewan. So during my work, I always had a very good and close collaboration with them. At KTH, my professor was Jörn Andersson in power system, and he was eventually moving to Zurich. But my mentors has always been a very important inspiration for me, and I've been trained from the beginning to have a very strong relationship to IEEE and PS, and I'd like to encourage all of you to get involved and to learn, because we that have worked for a long time, we want to share our experience and knowledge, and I think it is the right way to go forward. So now I come to the more technical part of my presentation, and I would like to come to an introduction of the topic. So who are we and what are the drivers to asset management in your view are some of the discussions we can discuss about. And what are the challenges? And in the introduction here, you were mentioning about the transmission lines. So that is something that I understand now, that is an important topic for you. I had included one more picture about where I come from. I come from Sweden. And the university I work with is called Royal Institute of Technology, KTH. It is the oldest technical university in Sweden, and electrical engineering was a topic initiated already in 1901. We have very proud, we have one Nobel Prize taker in history, and he was actually working in the same house that I am, so we are very proud of that. We are around 5,000 employees, around 13,000 full-time students. We actually have one specific collaboration with India, and I know we have a very good exchange of students, so that's very nice. Here is just a brief, you already made a very nice presentation of me. I just want to reflect about that I come from Sweden. I spend quite a lot of my research time in North America. But I also been traveling a lot, and I feel that it's very important for us to exchange our knowledge and experience and meet. So I'm happy that I've been in India twice, both in Bangalore so far. And here is just some more information about myself. You already gave me a very nice presentation. Maybe this picture that you can see here is something new. And for maybe some of you are excited about power system reliability. And in that case, I would like to recommend the conference. We call it the family conference. It's a PMAPS conference. And I was very happy to be the chair for that conference many years ago now. And this is a picture from that, 2006. This year, the conference will be in UK. So back to the technology area here. We are seeing a large development. We talk about the transition in the society, in the energy system. And the power grid is a facilitator in this transformation. All of us today here, I think we are familiar with the concept of energy and electricity, but we can see around us that it is a very large confusion. And in my role as a professor, I have quite a lot of communication with politicians and with journalists, etc. And I always try to support and help them because it's not so easy to understand the difference. So that's why I always start all my kind of presentation and just remind people that energy is something that's transformed and transported. Electricity could be in either an infrastructure for energy, but we also see electricity as a fuel, as a new type of fuel. Electricity is something we can produce, but energy is something that we are just transforming. So that is, yeah, good to remember because it makes us to understand the different challenges. So we see a couple of new trends here. Electrification, we see storage is coming. We talk about the circular economics that I wanted to stress at the beginning, because it means that we have this drive to lifetime extension in all kinds of aspects in the society. And we also talk about the digitalization. For the coming years, we see that there is an expected major need of investment in the electric power system worldwide. It can either be a result of an aging infrastructure from the need of expansions, or it could be a result from the transition to a sustainable energy system. Now, some numbers here are from the US, where they expected between 16 and 25 to have around $107 billion invested in this topic. In Europe, for example, we have a 10-year strategy plan where we can see around 150 billion euros in investment in the power infrastructure. If I look in Sweden, where I come from, the investment plan for the national grid are around 300% increase compared to what we have today. So we can see in front of us a huge investment, development, both in exchanging the existing system, but also building new. So now I would like to move forward in my presentation and discuss a little bit about maintenance itself, and how it can be used as a strategic tool. The definition of maintenance, asset management, can be like this. The aim of asset management is to handle physical assets in an optimal way in order to fulfill an organization's goal while considering risk, where the goal could be, for example, maximum the asset value, or it could be maximum the benefit, or minimal the life cycle cost. And risk, on the other hand, it could be defined by the probability of failure occurrence and its consequence, for example, unavailability in power supply. Related to the asset management, there are a lot of different actions. We need to acquire, we need to maintain, we need to replace or decide. So the asset management, it is very much around taking decisions, smart decisions on what assets to apply the actions for, and what actions should be applied, and how to do this, and when to apply the actions. To make the right decisions, we need a lot of information. We need the condition data. We need failure statistics. We need reliability modeling techniques. And we need reliability assessment tools and maintenance planning tools. And also different kind of systematic techniques for maintenance planning. For example, reliability-centered maintenance that I will discuss more in detail in this presentation. What I want to comment here is that if we look at asset management, at the end, it's very practical. We need to make a decision. So independent on what availability we have here, we will take a decision. So in a lot of circumstances, I would say that it's very important to get an understanding of that we have to base our decisions on the best available information we have. In a lot of different contexts, we don't even have failure statistics. I had a meeting prior today with some people with very knowledge experience in transformers. Transformer is a very crucial equipment in the power system, and transformers are highly reliable. So we have a very, very limited failure statistics, which is good because it shows that it works. So we have also to be aware that the decisions and the methods we develop, they will look different depending on the situation we have. But we can always talk about what is a perfect world, what we like. But we really need to understand that independent of what we get, we will still make a decision. So we should try to support to make the smartest decision on the material we have. I want to spend a few words commenting on a standard. It's called ISO 55000. This is the first international standard for asset management. And some people, maybe some of you or other, they are familiar with a previous, it was not a standard, but it was a similar content, the PAS 55. This comes from the British Standard Institute, so it was not a global standard. And it was resulting from an effort by the Institute of Asset Management. And that was considered the first international specification. So what the major difference from the PAS 55 and the ISO 55000 is that the ISO 55000, it's a standard for any kind of asset. It doesn't really has to be a physical asset, even though that's what we discussed today. So if you work with asset management, I recommend you to look at this standard because it's really important that we try to use same terminology, and it makes it easier also when we develop different tools to help us in doing asset management that we are following in the standards. So a little bit more details about the standard. It is actually what we say a family of standards. So it's a couple of them very connected, and they are aligned with other major systems. For example, the ISO 91 is the quality management standard. The ISO 14001, that's the environmental management, and the ISO 31000 for risk management. For an organization, this could be very important because maybe they have already signed up to follow some standards. So then it's important to know that they are aligned. Another feature of the ISO 55000 is that it's following a standard. That's called SL. It's a kind of high-level structure, and it's helping to provide a universal structure with an identical core text. And this would be more relevant for people working with how you can implement this in your organization. If we look at the terminology within the ISO 55000, I have highlighted a couple of words that I believe are most relevant for our talk today and our work in asset management. We have, for example, the asset, how we define the asset life, and the life cycle. The life cycle stage is involved, the different stages involved in the management of an asset. We also talk about preventive and predictive actions and the corrective actions. When I discuss about maintenance, I normally want to underline that we have fundamentally the two different. We can either do corrective action or preventive action. In reality, the corrective is to do nothing. We just wait for the world to happen. But in the preventive, we can do smart things before something happens. So the focus would logically be on the research, trying to do smart preventive, because that's where we can do smart things ahead of something happening. So the predictive is a type of preventive action where we can monitor the condition of an asset and predict the need for preventive action or corrective action. This is one of my favorite pictures that was created by one of my former mentors that unfortunately they're not with us any longer, John and Rennie. And I believe it's a very nice, simple way to communicate what we're trying to achieve. So what we're trying to achieve here is to increase the asset value. And we will increase the asset value by making a decision on alternative policies. And in the figure here, you see the three different policies. One is to do no maintenance, and that means basically corrective maintenance in this terminology concept. And the other two would be comparing two different alternative policies. So the target we are trying to achieve is to reach an incremental asset value. That is the target. So consequently, we can say that maintenance is a tool for asset management. And it can be defined as an activity of restoration where an unfailed device has its deterioration arrested, reduced, or eliminated. The goal we have is to increase the duration of useful component life and to postpone failures that typically would require expensive repair. Consequently, the task of maintenance is to slow down the deterioration process. And this is what we would show in the figure, where we see the decreasing of the asset value. And the curve says what we call a life curve. So the coming pages here is going a little bit in detail on how we can compare these different policies. So maintenance, it is an integrated part of the planning, construction, and operation of the system. Moreover, they are central and crucial importance to the effective use of available equipment. The aim of maintenance activities is to continuously meet performance, reliability, and economic requirements, whilst also adhering to the constraints set by the system or requirements by the customer. Functions are what an asset is expected to perform and can also be anything an asset has to comply with, such as the color or shape. The function of an asset does not have to be exact. In some cases, it's sufficient if the performance of an asset lies within an interval. For example, if you look at an oven, it has to provide a certain temperature within an interval. And it's possible to divide the functions in two categories. The primary function that describe the main purpose of the asset, and the secondary function that describe the additional features that the asset should meet, such as a color or safety aspect. And here are some more terminology that are important to understand and use in a consequent way. We have the functional failures. And this is the inability of an item of equipment to fulfill the functions. But then we have the failure modes, and that are the events that cause failure functions. And this might sound obvious now, but you will see later on in the cases that sometimes it can be difficult to understand what are the differences here, but it's really important to separate them, to understand the logic of what we can actually do. So the failure effect, that's what's happening when a failure mode occurs. And the effect, we can divide them into evidence of failure, of safety, and environmental hazards or production effect. Then it comes to the failure consequences. And the consequences of failure, it can be classified as hidden, etc. So let's see. Oops, I have a trouble to read down here. And then we have potential failures. Oops. That we obviously don't know before they occur. The coming pages here is defining. This is a method to define because we have this time. If you look at the graph here, at time F, we have a failure. And at time P, we have some kind of potential failure. It's something we can measure. So what we're trying to do with our methods, our models, is trying to get in information in order to do something smart before ahead of the time F occurs. And here is a little bit more description of that. I go that a little bit fast, and we can read afterwards. So many failures, then they can be classified as an age-related. This kind of failures are often found on mechanical equipment, for for example, due to fatigue, corrosion, oxidation, evaporation. To be classified as an age-related failure, the probability of failure should increase at some point in time. The increase of failure probability can, for example, be constant in time or start at a specific age when the component usually wears out. Then we have non-age related failures. They are not due to age, but rather to the surrounding factors. It could be non-uniform stress or handling errors. And for these failures, there's no certain point in time when the likelihood of failure increases. We can also discuss about hidden failures. This is failure is not noticed under normal working conditions when the failure is a hidden failure. And these failures alone are often a minor issue, but in case of multiple failures, they can be disastrous. Failures of safety equipment are often classified as hidden failures and will not become evident until there is another failure. So this will be a really challenge to find these failures. Maintenance is a combination of all technical, administrative, and managerial actions during the lifetime of an item, independent to retain in it or restore in it, or state in which it can perform the required function. And it can be carried out in different ways. And here is the figure that I think I was mentioning before from my mind, that we think about the maintenance with the two either alternatives, either the corrective maintenance or the preventive maintenance. If we select the corrective maintenance, it's not really something more we can do. When something happens, we will take care about it. But in the preventive maintenance, there are a lot of possibilities to act on those. Traditionally, we use something called predetermined maintenance. It's when we have a schedule, it's a plan. And this will be a very traditional way of doing maintenance. When you buy an equipment, you will get a book and it will say maybe every year you need to oil this function or have a visual inspection, etc. So that is a very simple and straightforward way to work on maintenance. The more advanced models, it would be what we call condition-based maintenance. And here you could do either a kind of continuous, where you're measuring something, you're taking in some kind of information, and then you take a decision, an understanding on the condition, and then make a decision about what preventive maintenance to do. The other alternative is that you have a schedule. But it's still related to the condition. And the third option would be that you have a request. And here it could be a kind of a flagging that you say, when the equipment has reached this type of condition, you should do this kind of activities. And this is following a standard for maintenance. And I truly recommend you to use this kind of technology because it makes it really clear. So preventive maintenance is carried out at 3 predetermined intervals or according to a prescribed criteria. And they are intended to reduce the probability of failure or the degradation of the function of a failure. The predetermined or scheduled maintenance, that is a preventive maintenance activity carried out according with established intervals of time or number of units of use, but without previous condition investigation. So the predetermined maintenance is an option if failure is at age related to the probability of failure in time can be established. Depending on the consequences of a failure, different maintenance intervals can be chosen. If the consequences of a failure are not too severe and the costs for predetermined tasks are high, one might choose to allow the intervals between the tasks to be longer than if the function of failure leads to a safety hazard, which has consequences that cannot be tolerated. And examples of predetermined maintenance tasks can be scheduled restoration and discard tasks. Then we move on to the condition-based maintenance, and this is a preventive maintenance based on some kind of performance or parameter monitoring and subsequent on the action. So when we deal with non-age related failures, typically the CBN tasks are used. And these can be performed by inspection, for example, And some common methods include using human senses, which is listening for unusual noise or condition monitoring of the assets. These tasks do not help to postpone a failure, but it can detect that a failure will occur and thereby make it possible to act in order to avoid the consequences of a failure. So it could be continuous, scheduled, or on request. And if it's scheduled, we can use the PF intervals that I discussed briefly before. Then we come to the corrective maintenance. That is taking, it will happen after a fault has been recognized, and it's intended to put an item into a state in which it can perform a required function. And CM is used if there's no way to detect or prevent a failure, or if it's just not worth doing. And it simply means that the asset is run till failure occurs, and then the system function is restored. This may, of course, not always be an option if the consequences of breakdown are very severe. To find out whether a hidden failure has occurred, failure finding tasks are used. This is done by checking if equipment is working in the way it should. These tasks can, for example, include switching and checking if spare equipment is functioning properly. Redesign is used if there is no possibility to conduct maintenance on an asset and the probability and consequences of the failure are too high. Redesign may also be advantageous if maintenance is too expensive compared to redesigning. And redesign is not always considered to be part of maintenance, but it's included here. So the aim of preventive maintenance is to extend the lifetime of the equipment. The component lifetime can be prolonged when the causes of component failures, and therefore component failures rates themselves reduce. This is of course dependent on the nature of the causes. And one way of understanding the relationship between maintenance and reliability would be study these causes. And moreover, the cost-effective planning of a system implies that the correct components are maintained at the correct time and with the correct maintenance activity. And in this context, this means focusing maintenance on the critical components that's chosen to have the most significant impact on the system reliability and to reduce the dominant causes. And essentially, there are 4 tasks that we can define in a scheduled maintenance program. We can do inspection of an item. We can rework an item. We can discard an item. And we can inspect an item. For each failure type, an RCM, that's the Reliability-Centered Maintenance Program, they should be able to determine the type of maintenance task, if any, that should be applied and how frequently. And decision diagrams, they can assist in this process. They are following typical maintenance questions. What efforts are required for this maintenance? And is the maintenance performance too little or is it correct? Is preventive maintenance done on the correct items? And what is the relationship between failure and maintenance cost? And applying the RCM method would be a way to provide answers to these questions. When we design, we should design already for the beginning and think about the preventive maintenance. The effective PM, it actually begins with a good design, because if you can't access, if you can't come in and enter in the system, it's really difficult. So you have to think about it from the beginning. And experience shows that equipment lasts longer and performs better when it is covered under a planned program. If we look at the equipment itself, the deterioration, it starts with the installation. And normally, and if unchecked, the deterioration can progress and cause equipment malfunction or failure. And harsh environmental conditions and system stresses, such as overload, severe duty cycle, load increases, circuit alternations, and changing voltage conditions, they can accelerate the deterioration process. And here I want to give an example. When I started to work on wind power, it was in the like 2006, 2007. And so this was in the beginning when the offshore wind was in business, for example. And what happened at that time is that it was a lot of failures in the gearboxes. So the first paper I published in wind power, it was on statistics. We could show from statistics on this very important challenge. And the reason why they were breaking was really much related to what's said here, because it was a very harsh environment. Because the gearboxes that existed at that time, they were not made. We have no experience of putting that kind of technology in that environment, and we can imagine that offshore it's the salt, and you have in the wind is very varying the load. So this is a very important aspect to think about. So an effective PM program, it can detect and mitigate these conditions. And we see that there are different basic functions that we need. Well, it's needed to keep the equipment clean, to keep it dry, and to keep it sealed, and to minimize friction. So these are criteria that are important. Finally, for this section, I would like to say a few words about data analytics. This has been a topic evolving the latest years. And when I talked in the beginning of different trends, one of this trend is digitalization. And as an effect of the digitalization, we see today that we have a lot more access to data. And with that data, we can do a lot of smart things. And the concept of data analytics is capturing that. So what is it really? Well, statistics, as we know, is a branch of mathematics, and it includes the different aspects: collecting, analysis, interpretation, presentation, and organization of data. And data, it's a set of values being either qualitative or quantitative. The qualitative properties, they are observed and can generally not be measured. But the quantitative properties, on the other hand, they have the numerical values. And the methods that I have in this tutorial, it's bases in the quantitative methods, because that's what our research is included. But it's my believing that a sound maintenance management, they require both of this type of data, since experience show that it's not always that we can express things in numerical values that are of importance. So if we continue and study on the statistical methods, we can divide between descriptive and inferential statistics. In the further, we summarize data from a sample using indexes. The data analytics term for analyzing this data, it is the exploratory data analytics, EDA. The EDA, it aims to find patterns and relationships in data. The latter, it draws conclusions from the data that are subject to random variation and are commonly referred to as probability theory. The data analytics term for the analysis of the data is confirmatory data analysis, CDA. And the CDA applies statistical techniques to determine whether hypotheses about a data set are true or false. So the DA, that is the process of examining data sets. And advanced type of DA, it includes the methods of data mining. And data mining can include the sorting of late data, identifying trends, patterns, and relationships. We also talk about the predictive analytics, that's seeking to predict customer behavior, equipment failure, future events, etc. Then we have the machine learning and artificial intelligence technique. And that uses automated algorithms, making it possible to solve larger problems faster compared to traditional methods. And finally, the big data, that is a term that's used to set that larger complex data that traditional data analysis methods and tools are not possible to use to get results with a tolerable elapsed time. And challenges typically include capturing, storage, analysis, searching, sharing, visualizing, querying, and updating. And these challenges might result, for example, that data mining is not possible to apply. And here is a definition of the big data. So maybe we want to have a short break here. Do you think so? Or how are you doing, everyone? Do you want to stop for a questioning time, or should I continue?
Ma'am, you can continue, and we'll have the question answer session at the end, if that's okay.
Okay. Yes to know, good to know you're with me. Okay, I will continue. Thank you, everyone. So can you just confirm that you see my screen again properly?
Yes, your screen is visible.
Thank you so much.
Yes, ma'am.
Thank you so much. So I will now continue with a next step in the presentation. And here I will go in a little bit in detail of a method that we called reliability-centered asset management method. And this method is outgoing from the RCM method that I mentioned very briefly. After that section, I will go back and share with you some case studies. So this part presents the generic method of reliability-centered maintenance and its extension into the quantitative approach that's called reliability-centered asset management. And this is an approach that I defined 2002 in my thesis. So it presents the different stages of performing an RSM. It includes the performing a failure mode effect analysis, FMEA, of critical components. And finally, it's also discussed the different needs of input data. So what are the RCM concepts? Well, the term RCM, it identifies the role of focusing maintenance on reliability aspect. And the RCM methodology, it provides a framework for developing optimally scheduled maintenance program. The aim of RCM, it is to optimize the maintenance achievements. And here we talk about the efforts performance in a systematic way. And the aim is to achieve cost effectiveness by controlling the maintenance performance. The RCM concept, it originated in the civil aircraft industry in the 1960s with the creation of Boeing 747 series of aircraft called Jumbo. The reason here, and here this goes back to my first, if you remember, I said the three things I want you to take away from this presentation, that asset management is a result itself from doing something smart. And it's the same here with RCM, because what happened when we created this, it was a big shift for the aircraft industry, the move into the jumbo aircraft. And they realized that it was not possible to do this if they would continue to do maintenance in the way they have done before. So it was a need to create a more efficient, more limited preventive maintenance. Otherwise, it will be impossible to make this change to increase the volume in these aircraft. It will be too expensive. And so it was really very successful. And the primary concern was to identify the maintenance tasks that would eliminate the cost of not necessarily maintenance without decreasing the safety or the operating performance. And the resulting method, it included an understanding of the time aspect of reliability of the aging and identify critical maintenance actions for system functions. And this maintenance program, it was a success, and the good outcome raised interest and the program spread. And in 1975, the US Department of Commerce, they defined it as an RCM concept. and declared that all major military systems should apply with this. And the first full description of the RCM was defined in 1978. It passed in time when I was writing on my own PhD thesis. I was borrowing at the library a document, this kind of report, and it was very nice to look at that originally and to see that what we are continuing to do now, it's fully continuing on that very same definition. From our side, from the power sector side, in the 1980s, the nuclear power industry started to introduce RCM. And from my own experience, we started in the 1990s, and we could see that it was starting to be used in the hydropower area. And today, I would say the RCM is under consideration, or it has already been implemented in many electrical power utilities for managing the maintenance planning. There are different versions of RCM, and in some contexts, maybe that's not so important, but what I want to underline is that the same key factors are still there, and I want to go show them in detail here. So this is the key factors, and this is what you can also read in this original document from 1978, that they have the 4 key features of preservation of system function, identification of failure modes, to prioritize function needs, and to select the applicable and effective maintenance task. There are different formulations of the process of creating an RCM process. And I'm listing here 3 different formulations. They are both coming from the original definitions. This is one defined by Smith, and here we can see 7 different steps in a process. System selection, system boundary, system description, where you use functional blocks, system function and functional failures, and then you see what I mentioned before, the FMEM, and then logic, tree analysis, and selection of maintenance tasks. I would say in the nuclear power, they have used typically this system. My experience from the nuclear power industry is they typically have used this kind of logic and tree analysis in their risk assessment, as we all understand that the risk assessment is very important in nuclear. So they have a very good tradition of using that. And I think that's why they're using it typically in this perspective too. Mowbray is another writer that has defined the RCM. And from that perspective, they formulate 7 questions instead. That would be, what are the functions and performances required? In what ways can each function fail? What causes the failures, and what are the effects? What are the consequences? How can they prevent them? And then select the activity. For those of you that have high intention here, you might realize that it comes back, because here are some of the aspects in the failure mode effect analysis. So you will see that the content here is really similar. It's just a different way of thinking when we are gathering the information. So the RCAM method that we have developed for our research, it has been developed on an understanding of the RCM concept, and also based on experience from a numerous number of applications. And I want to underline that because I truly think that we need experience here, because this is not something that's easy movable from one topic to another, because we need to understand the specifics, what is specific for high voltage equipment. And with that experience, we can contribute to the methods. So the RCAM identifies the central role of defining the relationship between the component behavior and system reliability. And that's made through the evaluation of the causes of failures. And the method was published in my thesis 2002, and since then is been applied for different various applications. For some of these applications, it's only a part of it that we are applying, because as you will see in coming pages, is that to make a complete RCAM is a very extensive work. So what we normally would do, both from a research perspective, but also I think from a utility perspective, is that we will select some equipment, some areas where we will go deep and make a solution. This is an overview of the method. And here you can see what are the different procedures if it's on the system or equipment level. And that is, I know from experience that that could be a challenge sometimes, because if people are very much into the equipment level, the component level, it can sometimes be difficult to see how it contributes to the system level. So this is not something that comes automatically. We really need a process to help to create this thinking on the system aspect. In the table, it's also included here, what is the data required and what are the results. And as I said before, it's very important here to see that we're moving from the system to the equipment to the system level. In the component level, we are focusing on what I call the critical components. These are the components that we have defined. This is a result from the first two system level. So those are the components that are most relevant for the system reliability. Then we will focus on understanding how we can impact on the failure causes, on the failure modes. And when we have that understanding, we can create a model for that. But when we have that model, we have to come back to the system level. And I include here sensitivity analysis just to understand where we are, because we will never have a true solution. We can only know within different scenarios where we are. And at the end, we want to do a cost-benefit analysis, and that is on the system level. So this is the whole picture. So the picture includes the main procedures, and we have the logic, the need for the interaction that I mentioned between the system and component level, and also indicate on what data we need. So there are these different stages, the system reliability, where we evaluate the critical component. Then on stage 2, we go and focus on the critical components, and we want to understand the component behavior and how we can impact that with different preventive maintenance activities. Then when we come back to the system level, we need to model the system and its impact of these different equipment. And at the end, we would like to have a cost-benefit analysis. For example, it's a life cycle cost analysis. So the central part of the RCAM and the greatest challenge is the definition of a relationship between reliability and preventive maintenance. And that is what I would say the stage 2 in the RCAM analysis discussed previously. This could be done through a generic approach involving the steps to be processed, or a generic theory involving mathematical relations to be solved. And here are two alternatives. Well, for the stage 2, this has to be related to what kind of information we have. And I define it as approach 1, where we are trying to create a relationship between failure rate and the preventive maintenance. And I use lambda as an expression for that. And the other approach is a more simple approach where we basically take in the information. Oh, no, this is the advanced. So in both of them, we're creating this relationship. But as you see here, in the approach 1, we are actually making more a general, because you see we don't have the time as an aspect, but here we include the time as an aspect. So this is a little bit more evolving relationship. So if we continue, the strategy provides a recommendation for performing an activity. However, on the actual day when we should do the preventive maintenance, the decision would be based on whether it would be beneficial to do it the same time at that day, or if we should postpone it, or if we should do something else. So there will be a layer of decisions on the strategy level. So the RCM method, it implies development of a policy based on our predicted behavior that should be used to set a policy for determining the procedure for the maintenance. I mentioned before about the FMEA, and FMEA is a useful tool when we perform the RCM analysis. It's a way to evaluate the potential failure modes and their effects and causes in a systematic and structured manner. Failure modes mean the way in which something could fail. And effect analysis, it refers to studying the consequences of those failures. So the purpose of the FMEA is to take actions to eliminate or reduce failures. So by itself, it's not to solve a problem, but it can be used with other tools. The FMEA could be made in different details. Either it could be a qualitative level or a quantitative level. And here I go through the different basic steps. So the first step would be to define the system and to make the boundaries. The second step would be to identify the different failure modes. For each of the function, we need to identify how the failure could happen. And this would be the potential failure modes. In step 3, we would identify possible effects of failure modes. For each failure mode, we could identify all the consequences of the system, what happens when the failure occurs. And step 4, we can determine and rank how serious effect it is. We will continue, and for each failure mode, we determine all the potential root causes. So root causes is kind of the underlying causes. And for each cause, we want to identify available detection method. And at the end, identify recommendation actions for each cause that can reduce severity of each failure. So the FMEA, it classifies each potential failure according to the severity of the mission success and personal or equipment safety. The FMEA could also be extended with the criticality analysis. And the CA will provide estimates of a system critical failure rates based on a past history and current information. The resulting FMEA is a reliability evaluation and design technique that examines the potential failure modes, which is system, in order to determine the effects on the overall system and the equipment within the system. It's important to reflect about here that this is not something we do at one time and then we have a specific result. Because the topic we talk about today is a topic that changes over time, because it will change depending on the stress on the environment or the time aspect itself. So it has to be a living document that been used during the total lifetime of the system we're analyzing. And generic maintenance data, it is a valuable tool when historical data is not available, or when we are establishing a maintenance-based line for a new system, for example. So the overall goal, it is to reach a systematic asset management process where we can use RCM and RCA. And this does not only mean to implement the models, but most important, it is about to find a process for updating the maintenance program. And it's worth underlining, the experience shows that it's challenging to reach this goal. And one example of that is, and I write that as a chapter in my book, is the experience from the hydropower sector. In Norway and Sweden, we have a very long, strong history of using hydropower. Originally, it's the core for our electricity production. But a hydropower plant has an extremely long lifetime. You would typically prolong the life by exchanging some equipment, so it will be never-ending lifetime. And the main owner of the hydropower plant in Sweden has been Vattenfall, the state-owned company. And in the 1990s, Vattenfall took a decision to make RCM for all the hydropower plants. So what was done there was that they were doing for each specific plant, they were going through an RCM process. It was a very good process. People involved learned a lot, and the outcome was very nice. But the problem was that it was a really extensive activities to perform this. And when it was finally done, the organization was a little bit downloaded with all these analyses. So then nothing really happened. And I wanted to take that as a learning that we have to judge from the beginning what we are really prepared to do, because it's no point of doing these extremely detailed processes if we can't manage, or if we're not willing, if we don't plan to work with it on the same detail level. Because it's more important to do the update than to have a detailed model. So we need to be smart and think from the beginning what we want to achieve. So the RCAM process, it starts in the design phase and it continues for the life of the system. And there are several major tasks required to implement the concept. And in order to make the RCAM analysis, it's a need for comprehensive knowledge of the system, of its components, and other input data. And this is a figure we will spend some time to look at it. And it's this figure has been further developed from a figure that's presented in a standard. It's called Gold Book. And I have extended it with the RCM perspective. In the traditional way of thinking of maintenance is the top one. We design and we develop. What is the new concept here is that if you look at the bottom, we talk about operation and support phase. So the new thing here is that we are claiming that we should work with asset management and maintenance during the whole process. So this should be a circular program. And we try to communicate here what is the content of the RCM analysis, what are the needs, input, and the output would be our different maintenance program. And the updating is extremely important because that's the way we can improve our system and improve the processes we work with. So according to the standard I was referring to, we can divide the task into the different activities of conducting supporting analysis. This is an information intensive process. And I mentioned before the FEMEA. We can also have the fault treat analysis as an input. And the other one would be to conduct the analysis. And here we can use, for example, the logic tree activity. We can do economical assessment, etc. A central part of the RCM analysis, it is on how we do collect, select, and define these different input data. And I mentioned before that we separate here on the system level and component level. So on the system level, we need description, we need drawings, we need to understand the control programs for maintenance. And we need to know commitments or requirements for the existing programs. At the component level, we need a lot of other details, for example, the list of the equipment, etc. For the cost-benefit analysis, we need other type of input. We need to understand the investment cost, the outage cost. We need to get information about the cost of undertaking maintenance, the manpower, materials, equipment. And also we need to understand the cost of not making maintenance. That's the outage cost, both from perspective, for example, in a grid, we would have the utility and the customers. With the input data, it also involves experience from practice. And they could be categorized in the two areas of understanding the overall procedures involved in the maintenance planning, but also a dialogue needed with the utilities to get to understand the relationship between the maintenance and reliability. At the component level, we need a couple of things to discuss. So which are the modes that can be affected by maintenance? And what are the relationships between failures and lifetime? And whether maintenance can affect if we have a constant failure rate or a wearing out. For the cost-benefit analysis, we have other inputs that we need to look at. So the RCM analysis, it requires an extensive amount of information. And much of this information is not available in the early design phase. The data we can look at are different categories: the failure characteristics, the failure effects, the cost, and maintenance capabilities and procedures. We also need to understand the failure characteristics, to understand if it is efficient to do preventive maintenance. For example, if we have equipment which has a constant failure rate, then it's not beneficial to do preventive maintenance. So we need to understand what is the characteristic for the failure. The failure effect, that is the effect of failure of some items are minor or even insignificant. The decision whether or not use preventive maintenance for such items is purely based on the cost. If it's less expensive to allow the item to fail than to perform preventive maintenance, then it's allowed to fail. If you look at the cost that can be considered for a given time, the cost of performing corrective maintenance and the economic penalties, for example. Maintenance capabilities and procedures also need to be understandable. So now I'm coming to my last part of my talk, where I'm highlighting a couple of studies, and I'm also giving you references if you would like to read more about them. And then I will save a little bit of time so we can also make a discussion. This is a picture it's myself, I'm a former PhD student, Francois Bernard, and this was a very happy working moment for us. We are standing this is in Norway, and it's a wind turbine. It's a 3 megawatt turbine, and it's the same model and brand that the one that we are doing other studies on, that's in Lillgrund. Lillgrund is an offshore farm. It was put in operation 2006. At that time, it was the world's largest. It's 120 megawatts. Today, it's definitely not the largest, but it has been running well since then. We had a very nice opportunity here to hang around and watch when they were doing inspection in this turbine. I felt that this figure is communicating quite well to understand the challenges here of performing maintenance, and still this is on land, so we could experience how it would be if we would be out on the sea. So it's obviously a very specific challenges in this application area. One publication from Francois' work that I highly recommend if you are interested in this area is a nice little optimization model that we developed. If you are considering an offshore wind farm, there are a lot of optimization questions, and one fundamental is what kind of vehicle you should use to go out there, and when should you go out there, when should you do maintenance. And it's very obvious that if you would like to make a smart asset management, you would like to reduce the number of times you go out. And if you go out, you would like to do as many things as possible. And that's why in this kind of application, we normally separate the equipment into large and small maintenance efforts. So it's known that if you would like to do a lot of efforts or not, and then you try to optimize it in the way to do as much as possible when you go out there. But the optimization here is to look at the transportation, because the accessibility is very much constrained by the weather. This is a result from one of our first publications. It's published in 2007. I mentioned this publication before because this was the first known publication showing on the failure statistics for wind turbines, where we could validate the experience that gearbox has of challenge both in the downtime and the failure frequency. Because as we know, the unavailability is the combination of these two parameters. So if we could find an equipment that has a high downtime and high failure frequency, that is for sure critical equipment. This is an example of another project where we started to take in information from the SCADA system. And with this information, we were getting alarms and warnings and being able to understand what was happening in the system, to get a kind of a flagging if something was not normal in the behavior. And the idea of the research here is to train up models that will give an indication if something is happening in the condition of the system, and it will give input to decisions of preventive maintenance. And this is the similar work showing a little bit more on the model that we used. So we have used artificial neural networks and to make a model. So what we want to do is to predict possible anomalies in the system. I wanted to show also an example on what I call the third stage 3, where we do the full analysis and look at the life cycle cost. And this is a result where we did study the Horns Rev. That's another offshore farm. And what we are trying to, our conclusion here is that we can, with the smart planning of the asset management, we can reduce the total lifetime cost. And you see here the life cycle cost for the years in front of us. And if I look here, this says that around 12% is major retrofits, for example. So it is known that smart maintenance can have a big impact on the cost. I had one a little bit more detailed results, and I think I will go through this. I will pass this actually a little bit faster. And this is giving more input, and this is also related to the thesis that I showed in the beginning. So the motivation here we talked about, we actually had the privilege also to visiting the Lillgrund, and this is my own picture that I took when we are actually standing up in one of these turbines. So what we are doing here is to propose an anomaly detection approach to define the critical components in the wind turbine. And here is another picture that I have taken, and this is Francois again. And here you can see even more and get the feeling on how it is to perform maintenance here. You see the crane is up here and delivering some equipment that should be changed. So this is a evolving of the method I showed just previously. So what we are doing here is that we are training an network, and we are using input from vibrations and from SCADA. And that information we are supporting preventive maintenance activities. And this is a little bit more detailed about the method. So we're looking at the short window of time between the indication of an impending failure and the eventual failure of the equipment. And if you remember in the beginning, I talked about this PF interval. So this is where we are studying. And any alarm of the vibration-based CMS and the condition monitoring approach will give information of the maintenance personnel so they can perform an on-site inspection of the specific component. And this is a little bit more detail about the model and some more details on how we have developed these models. And you're welcome to read more about this. So what we do here is basically that we are using the alarms that can trigger when a component signals exceed a threshold limit. We can indicate the changes of operation state and component malfunction. And it also requires the operators to take action to avoid severe damage. The alarm logs, they record the information on alarms that happen during the operation process. They can detect and acknowledge time, error numbers, text categories, etc. So the approach here is look at the SCADA as an input, and the data would be two parts. It's the operation data and the alarm data. And here are some more details on how we have worked on the modeling, on the pre-processing modeling, and about the NARCS model. And here is an overall figure trying to show developments in the stages in the model. And I will not go in detail here. So the summary here is that we have used the models for two different wind turbines. They have the same manufacturer, 2 megawatt rated, and they're onshore, located in south part of Sweden. We have used the gearbox in the turbine, and it's a planetary gearbox. And this combined with a two-stage parallel shaft gearbox. And this is a common configuration used in wind industry due to its large ratio and power capacity. And we have taken several parameters such as bearing temperature, lubrication oil, and oil pressure, and they are monitored in the SCADA system. So here you can see a figure, and it's also noted here in red where we take in the data, and the data was, for example, generated power, temperature, and rotor rotations. So the proposed approach is applied, and we also have a real data we have applied it for. There are two neural networks. We're focusing on the bearing temperature, lubrication oil. Then we have selected 4 attributes, which are the nacelle temperature, the rotor speed, the ambient temperature, and the grid production. And we're using 1 year for training. So here is just showing a little bit more how we do the modeling and the output. And what we are finally doing here, I go in here in the summary. So what we have done is presented this approach, and what we are doing is basically that we are indicating a potential failure before it happens. And we have been validating it with the data. So I would like to make a summary here, and then we will have a little bit more time to have a discussion. So what I have been discussing about here and trying to communicate with you is that asset management its targeting to make smart decisions. And this itself is important for the sustainable development goals. The standard provides a basis for implementation of asset management. And we are showing on reliability analysis and maintenance that they are efficient tools for asset management. We are also showing that it is beneficial to apply maintenance strategies based on the results of quantitative systematic techniques, such as RCAM and also life cycle cost, LCC. We want to stress that performing an RCAM is part of the design process and also of the operation and support phase. And also, we want to underline that condition monitoring is important input data for making asset management. So I think I will stop there and take questions for you. And for those who know, I also work as a volunteer for IEEE, and I'm actually a candidate for the upcoming president-elect. So you're very much welcome to vote for me. And if you have any type of questions, I'm here now. And I think I close my presentation so I can see. Let me see. Thank you so much.
Thank you so much, ma'am, for such an insightful and enlightening session. I hope there was a lot to learn for the audience today. Also, we would now like to open the floor for questions. So all the participants are required to put their questions in the box, or either you can unmute yourself and ask the questions. So, ma'am, we have a question from Bhargav, and he is asking what are the benefits of asset management?
The benefits of asset management, I would say that the benefits could be seen in different layers. The overall benefit would be that it's an economic benefit, I would say, because you're increasing the value of the assets you have, you will make smart. So at the end, it would be an economic benefit. But I also think that economy is not the only measure of things. So the other impact I think is very important is that if we would follow an asset management process, we will increase the knowledge within our organization of how we handle our assets. And I think that knowledge will itself improve what we're doing. And I think it also will stimulate people. And in order to maybe explain what I mean, I can share you from experience that when I was, for example, working in my PhD studies on distribution system maintenance, we were collecting data. And if you collect data from maintenance efforts, there will be people working, technicians working, they would report the data. And we were collecting that data, and sometimes you could see that they were lacking information in the reporting system. And what we realized is that it's very important to communicate to everyone within the process of why we need the information, what it's used for, because it motivates people to do it. And I think the asset management method that I'm trying to communicate here, the flow of it, that it goes round, that it captures the whole process, it also gives a feedback to the people. Because if you are spending your working time to report things, I think it's very important that someone tells you at the end that this was very useful information. We have used this information. So I think asset management gives a value in different levels. So it gives a feedback to everyone that's contributing that is important. And that will increase the quality of the work and be stimulating for everyone. So I think it has that feature too. Yes, I hope it answered your question.
Thank you, ma'am. We have another question. How can we go about electric power system reliability and asset management?
I'm not sure if I understand the question. Do you mean specifically how we do asset management in electrical systems?
Yes, ma'am. About electric power system reliability and asset management.
Yes. Well, I think we always need to look at our specific case, because I mean, a lot of these models, the generic models, they have the different actors, and in reality, when we take decisions in this topic, we have a specific case. So if we, for example, if we have the perspective of being a distribution system operator, then we are basically owning distribution grid, and our customers will be typically households, or if we have medium voltage, it could be maybe a subway or hospital or something. So if we look at that perspective, we would see what would be the benefits. Well, benefits here would be that if you are owning a distribution lines, it's a lot of your equipment are just lines. It's feeders, and then you would have connections, you would have protections, transformers, but you don't have. You would have it's an infrastructure. So you would do an investment, and then you're operating it, and it will be quite difficult for you to have a lot of money to invest in improving it, because at least in most countries, it's a kind of a regulated system. So the tariffs that the distribution system operator are taking, they can't just increase. You have to motivate them, which means that all kind of investments you do, you have to make sure that they are used efficiently. So from that perspective, I think the asset management method, it's important for the distribution system operator to get a view to understand in their investment. Because normally, well, I shouldn't say normally, but it could happen that if you do a large investment today, you will win in a longer time. And that's what, if you remember the picture I had on the life cycle cost in the wind turbine, what we try to communicate is that the total cost over the time, it could be lower if you compare different strategies, even though you have a lot of high investment and the starting time. And I think these kind of tools here, it helps us to communicate that, because for the person to take the decision, it can be difficult, because you at the moment you take a decision, you might need to take a decision that it looks like it will cost much more because in short term it will cost more. So I think the asset management helps people to take different decisions. If you instead would be owning a wind turbine or a hydro plant, it's a different perspective, because then you're selling your production. So if you're selling your production, it would be more obvious that if you have an equipment and you're generating electricity, you would lose money if you're not producing. So in that perspective, I would say in some aspect, it's easier to see that everything you invest that will keep that function will give you funding. So I think it is a little bit different perspectives depending on the technical system. But at the end, it's the same message that these kind of tools I'm describing, they will help to take decisions that are more long-term, that will give you a lower cost over time. That is the point. That is, I think, the key point. Mm-hmm. Thank you.
Thank you, ma'am. We have another question from Dikshita. What are the advantages of RCM?
The advantages, I think advantages is, in general, when we have a process, it's an advantage because we, all kind of systematic processes has an advantage, because if we repeat them, if we do them again, we can do it in the same way. So we have it helps us to be able to compare. So I think that is in general an advantage to have a systematic approach that you can compare. And that's why it comes with that it's really important that you will repeat it to do it again. And you can see trends. So I think that's one. But we also want to add that the driver originally to create RCM, and I mentioned with the aircraft industry, the driver originally was to reduce the cost. So I think we have to remember that has been a drive from beginning, and the drive was to reduce the cost but still have the same quality. It's obvious from an airplane because you don't. I mean, it's obvious we don't want it to fall down, but for the power system, it's not always obvious in the same time. So what RCM did, that was a change in understanding, is that it says that it's the function of the system that's important. It's not the function of the individual equipment. And for us now sitting here, maybe it's obvious, but I would say that in past, in our sector, it was a lot of people that were experts in the equipment. So for them to move to a thinking that it's the system that's important, not the equipment, that is a change in thinking. So I would say that is a change. So the RCM would help us to focus on the system function. Mm-hmm. Thank you.
Thank you, ma'am. And our next question is, how renewable integration to grid affected the asset management?
How the renewable will...
Yeah, how renewable integration to grid affected the asset management?
Well, it's an interesting question. So how would renewable integration impact? I think technically it will impact quite a lot, because when we integrate renewables, we typically think about wind and solar. And wind and solar, they have a characteristic when they change frequently within the time aspect. And this will impact quite a lot on the aging, I would say. It stresses the system much more. And I really like this question. This is a very good question. But I would really say in summary that the impact is that it will increase the stress on the system. So I would say in overall that it will make even more important to look at these questions. And it also, if you say like this, it also makes it even more important to think about the long term. Because when we talk about sustainable development, one part is renewable, but another part is the circular economic. And in the circular economic, it means that we should be very careful using our resources. So we don't want to waste anything. We want to reuse materials, batteries, etc. And here, asset management have an obvious critical role that's giving more attention. So I think in future, I would expect to see that connection even more clear. But for me, it's obvious, very obvious. So thank you for that question.
Thank you, ma'am. So we have our next question. So it's, what are the principles of asset management?
The principles?
Yes, ma'am.
I think some of the main principles, it is that we look at the system perspective. That is the very main, and the other would be that we are not, when I discuss the failure mode effect analysis, I think that defines key concepts, because we have to look at the failure mode, the failure functions, the failure causes. I would say that's a lot of principles. But in general, on asset management, it's also, of course, the economic part of it, that we have to look at the impact, economical impact. But here I want to say again that it's in future, the environmental impact is maybe in the same level. So I would say that asset management, it gives us a framework to do smart decisions on all those aspects.
Thank you, ma'am. So we have another question. And if we know the criticality factor of each components, we should use the optimization techniques or not?
I mean, if we know the criticality, we would do a priority list. That will be the next thing to do. So if we first define the critical equipment, then we make a priority list, and then we will focus. And it depends. At the end, it depends on our situation. If we are planning for a long-term strategy, or if we are planning what should we do just now. But if we have a criticality list, I would say the first thing to do is to do a priority list, I would say.
Okay, thank you, ma'am. So we have another question from Rahul. He's asking which devices require more maintenance in power systems?
Well, that is an interesting question. So which devices requires more maintenance? When we look at the power system, it's different areas. I mean, we look at the distribution area, we can look at the transmission area, or we can look at an area where we also have the generation. If we look at the overall power system, the key equipment would be the transformers, I would say, because without transformers, we will not be able to communicate between the production and the consumption, because it lays in the fundamental idea of power system that we generate and we move it on a high voltage. So I think transformer, it will always be key equipment. But obviously, the lines and cables are, I mean, fundamental, otherwise we can't move it. But on the other hand, the protection system is very, very important, because then you disconnect it. And if you are considering also the generation, of course, that the function in the generation, I mentioned before that, for example, in wind turbines, it has been a lot of studies that could say that certain equipment within the turbine is more critical. But I want to add another layer here, that if I just compare to my own country, we have a country that's quite long distances, and we have a coast. One coast is in the Baltic, and one coast is to the Atlantic. And when we look at the maintenance, we would have different strategy for maintenance if the equipment are located on the east or west coast, because on the west coast at the Atlantic, it's much more salt and the winds are much more rough. But on the east coast, it's less salty and it's a little bit more softer climate in general. So when we comment on the equipment, it's important also to see where it's located, because the environment, geographic, is very much impacted. So I think that I would like to add that as well. Thank you.
Okay, thank you, ma'am. So our next question is, how reliability and asset management are related?
Well, the relationship between reliability and asset management is through the causes of failures, I would say. Because the causes of failures, that is how we can do an activity, because we want to do an activity to impact on that cause. And if we impact on that cause, we would change the behavior in the equipment. And that behavior would impact on the reliability of it, on the lifetime on it. So in some way, the reliability will have to start on a quite deep level, on the equipment level, in order to make the models. But in all of these kind of assessment, it could be different layers. Because if you are high in management level, probably they will not go in detail in equipment. So in that case, the reliability maybe will be more based on like an annual average or something like that. But reliability would be a key, because it will be a measurement that you could measure on the impact, I would say, on asset management.
So thank you, ma'am. So our next question is, what are the challenges of asset management?
Well, the challenges of asset management could be different in different layers. One fundamental challenge, I would say, is that it's not visible on the management level. Because if asset management is not part of the like management level in the company, then it shows that they're not using it as a strategic tool. So if you put asset management very far down in the organization, for me, it's a very clear indication that they're not considering it strong enough. So I think that is a challenge. But on the other hand, if you put it on the strategy level, but you don't have people that really understand your technology, you will not manage to keep the connection to the technology. So that is another, I think, challenge, that you need to get the connection throughout the organization to your equipment, but still to have it up there. So I think that is a great challenge.
Thank you, ma'am. So our next question is, how asset management reduces economic burden on the country?
The whole purpose of asset management that I wanted to stress as one of my three takeaways is that it will improve on the economic side. That if you do a smart asset management, it will reduce your overall cost, and in that way, it will be good for everyone. I believe that cost is not the only measure here, that we should also look on the environmental concern, and what we mentioned now is circular economy. So for the nation, for a country, I think asset management, the idea of asset management will help in give a long-term smart way of planning your technology to contribute to both to lower to cost efficiency and environmental efficiency.
Thank you, ma'am. So I guess it's our last question.
Yeah.
So thank you so much, ma'am. It was indeed a very interesting and a great session. So we have a small token of appreciation to Lina, ma'am. I request Rashi to present the virtual plaque.
Oh, that's very nice. Thank you so much. Thank you so much. That's
Thank
very
you, ma'am.
nice. Yes.
Thank you, ma'am. Thank you, ma'am. This is Arun Kumar. Definitely, I will refer your book, madam, on asset management, and definitely I will try to incorporate one subject on that, because it is completely new topic. We have studied on reliability. We have topics on reliability, but we have not included any subject on asset management. I will contact you within few days, and I will try to collect which course you are offering on asset management in your university. I will go through the website.
Yes.
And definitely we will incorporate this book as well as the contents in our curriculum, madam. It is very interesting and helpful. Thank you, madam. Thank you for delivering this webinar. And definitely I will keep in touch with you regarding the research, because we have worked a lot in reliability. So now we have to connect this reliability to asset management, because from asset management we can achieve reliability as well as security. So that is what I think. Thank you, madam. Definitely I will contact you in the future, madam. Thank you, madam.
Thank you for your kind words, and thank you for inviting me. And if you want to get in contact with me, you can send an email, and I will try my best to answer you.
Thank you, sir.
Thank you, ma'am. Yes, definitely I will send an email, madam.
Thank you.
Thank you, ma'am. Now, I would now request everyone to just switch on their cameras for a group photo.
Yeah.
Please, everyone, please turn on their cameras. I hope you have taken the picture. So Now, I thank you everybody for attending and participating in today's event. There's a link posted in the chat box for the feedback. So kindly fill in the feedback form and tell us how you like the event and help us to bring about more contents like this. So once again, everybody, thank you. And now everybody may leave the meeting.
Thank you so much. Bye-bye.
Thank you, ma'am. Thank you, ma'am.